So, welcome everyone. Thanks very much. I'm Dimitris Pezaros. I'm a professor at the University of Glasgow, and delighted to welcome you to Glasgow, where we're currently celebrating our 575th anniversary this year. So I'm very happy to be sharing the stage with one of my colleagues, Marco Cook, and then share some insights from our research on critical infrastructure resilience and cybersecurity, and how can AI and machine learning help in that, what sort of data modalities we have in these environments, and what are some of the system's challenges. As a starting point, I wanted to basically show this timeline, which is the timeline of our Glasgow Cyber Defense Lab, which I'm director of, and we started about 10 years ago, which is when CYBERUK and CSC about the same time came together, and not least to see how these the priorities that came from our funders and industry at the time have evolved over this timeline. So we started by looking at digital forensics and how we can do forensics in environments that are very resource constrained without disrupting their operation, how to do asset management in these environments without the process itself impacting and denying service to them. Then we started looking at how technology evolution and industrial technologies like industrial wireless might impact cybersecurity, to then incorporate aspects of organizational resilience and cyber awareness and human-machine teaming, as we've heard before, all the way to start looking more data-driven and AI-capable approaches to actually characterize and profile these environments and be able to do better detection of adverse events and attacks. And now we'll see all this coming together. It's not that we prioritize or deprioritize things across this timeline, but just showing how we're moving into a more systematic and more holistic approaches, focus points to improve the resilience and cybersecurity posture of critical infrastructure. So when we talk about critical infrastructure and what are the challenges, nowadays everybody has a much better understanding of CNI and the systems that comprise it than they did a few years ago. But basically it's the convergence between what we say operational technology systems that control physical processes and in themselves are not necessarily so intelligent, or they don't have so much capacity, with generic ICT capability to make the process of CNI operation more modernized, more efficient, to support decarbonization and other objectives. But this sudden connectivity, as we say in these environments, exposes them to threats and the landscape that they were never designed to deal with. So how do we protect them? Quite a lot of the environments we're looking at that include energy and water management and wastewater management and defense, sometimes and traditionally have relied to physical protection almost exclusively to protect themselves against adversaries. And this is not enough. The challenges that we're seeing is that across all the 13 critical infrastructure sectors in the UK, we have mission and safety critical systems with requirements that sometimes might not contradict, but by be orthogonal to cybersecurity. So safety systems, for example, that require operational efficiency, patching, which is non-trivial in these environments because of the safety cases that the components need to satisfy. The legacy that we have in terms of equipment in these environments and the time scales over which, for example, power station remain in operation and so on and so forth. And not only that, there is also the complex regulatory framework across the CNI sectors that makes things even more complicated to align, and the assessment standards that focus on trying to promote design time resilience and security, which is good, but it's necessary and not sufficient condition to protect the dynamic operation of those systems. So how does the landscape evolving in terms of attacks? If we abstract a little bit and conceptualize the cyber kill chain, we see complex advanced persistent threats or chains of APTs in these environments that start from an infiltration to an industrial system or to an IT system, then pivoting to an operational technology network and system, and then causing disruption. So these are conceptualizations of two relatively recent attacks on water treatment testbeds. And these attacks are put together by potentially state actors, and it becomes an engineering problem for them to attack critical national infrastructure. So the trouble is that when they get to it, depending on what resource they have, they might actually be successful. And then the question becomes, what do we do then in order to defend against this? If we look at the sort of timeline of how these attacks have evolved over the years, we can see that we start from attacks that have been very much targeted and tuned towards specific systems and specific physical processes all the way back to the Stuxnet days. But what we also see is the commoditization of these types of attacks. So attacks that can be generalized across, for example, programmable logic controllers, or living off the land attacks that basically disrupt the communication of industrial protocols without even having to be installed on the systems we're talking about. And if you're following the discussion on the Anthropic latest models, there is now potential for engines or models to generate lots of zero-day vulnerabilities that might impact industrial systems. So what have we done and what can we do to do better at protecting critical national infrastructure? And we're advocating that we need to try and build capabilities, cybersecurity and resilience capabilities into the systems, rather than trying to bolt them onto the systems once they are in place. And trying to do this and trying to retrofit capability to systems that might have a prolonged lifetime without having to cause significant changes to the physical environment. So at the moment, for example, what you see here is a conceptual digital substations and the digital substation and the different layers across the Purdue model that would make this work. If we wanted to have, for example, even encryption on some of the ID devices and processes at the lower levels, we would have to rewire a significant part of the topology. What we have been doing in the lab is trying to find ways on how we can have this capability built in without only being able to target attacks that we know about, attacks of last year, but also be able to use some machine learning and AI to profile the behavior of these systems, and then be able to develop the defenses in terms of prevention, detection, and mitigation, where and when required. And what you see in these diagrams here is a simplified MITRE attack track of infiltration, lateral movement, reconnaissance, and disruption, and how modular mitigation could be developed at different places in the Purdue model, where adversaries might have a sort of point of entry. We advocate that we should do that in terms of exploring softwareization and modernization of the infrastructure, and we have developed systems that we're demoing in our stand G3 if you're interested. We do realize that we have to be able to carefully deploy and validate those systems when we do, but there are ways of modernizing the infrastructure and doing it in a way that is secure. So in terms of our research program and what we're trying to focus on, we are concentrating around 3 pillars. Develop technology that will allow better visibility into these industrial environments and systems that underpin critical infrastructure environments. and allow real-time monitoring and instrumentation that would enable us to characterize their behavior and then react to adversary events. Then, once we have this visibility, what can we do with this data? And what algorithms can we run to detect, defend, and recover from attacks? And then how can we embed this technology into organizations, but looking at aspects of human-machine collaboration, regulatory frameworks, and so forth. So I think with that, I'll pass on to my colleague Marco, who's going to take us through a little bit of AI and machine learning in particular, and explore a little bit the data-driven cybersecurity approaches that we have developed, focusing on these environments. Thank you.
Thank you, Dimitris. Okay, hi everyone. So yes, as Dimitris said, I'm going to unpack a couple of the themes that he's just touched on. In particular, I'm going to explore the data modalities that are specific within industrial environments, and then how we use these data modalities to further enhance active cyber defense, detection, mitigation, and so on. So I'm going to focus first on data modalities. Now, industrial environments have an array of different data modalities, different data types, right? And these different data types offer different insights into the behaviors of the underlying systems, right? Now, we've got some examples here of data that you would find within these environments. So host-based systems data, this would be used for your kind of conventional host-based intrusion detection, so diagnostics logs, process files, and so on. Network traces, which provide indications of which edge computing devices, so industrial edge devices, are communicating with each other, so we can use this data not only to fingerprint the activity of individual devices, but also how these devices communicate across the layers of the Purdue model. And then finally, process data, and this is the kind of more industrial specific part of data modalities in this talk anyway. And this involves data from sensors and actuators that are part of the underlying physical processes that underpin CNI services that are typically stored within controller memory and things like this. So why is data modalities important? Well, I'll come on to the benefits in a couple of slides, but the main motivation here, kind of captured by this diagram here, is that attacks in OT can occur at, of course, different layers of the environment, right? And observing and capturing these data modalities in isolation can often mean that we miss more subtle attacks, right? If we only look at one modality or that modality in itself. So let's look at a specific example within industrial environments, okay? So within industrial environments, we have programmable logic controllers. These drive the underlying physical processes, as we've mentioned a couple of times. And they take data in from sensors and actuators, and they use this data alongside what's called PLC memory registers, right? So this is where they store the data from the sensors and actuators in the physical process. This data, these registers are also used in what's called the control logic of the PLC, or the ladder logic, which is what people might be more familiar with. And they use this to create dynamic states and evolving behaviors and control user-defined functions, such as controlling the generators or controlling water flowing from one tank to another, right? So this data exists in PLC memory. This is what PLCs use to drive processes. It's very dynamic. But this data also exists in a different modality, right? And that's the network, right? So we have the sensors and, we have the registers themselves on the PLC, but we also have data regarding the registers traversing the network between different PLCs. So an example in this case would be if we had one PLC that was monitoring the temperature of a generator and another one that was receiving that temperature and then performing some cooling functions, right? There's an obvious dependency, right? So there's an obvious link between data modalities here, right? That we want to exploit. And this is part of the fundamental research that we're doing at the University of Glasgow. So Moving away from data modalities, the question then is, how do we then use this data, right? What can we do with it? Why does it benefit us? Why do we care about different modalities within operational technology? And in the Glasgow Cyber Defence Lab, we've been actively investigating the interdependencies, the relationships between these different data sources, and how they can be used in synergy with machine learning, more advanced AI capabilities to, as I said at the start, provide more accurate, more timely, and also more informative detection and mitigation solutions within operational technology. Now, there are a couple of challenges with achieving this, right? We're not going to go over all of them today, but one particular challenge which often comes up in this area, in the area of OT, is the challenge of resource-constrained environments, right? So we don't have the ability to offload our machine learning, our AI algorithms for detection and mitigation onto the industrial edge devices, right? Partly because they don't have the interface to allow this, but also because of their resource-constrained nature, right? Nor can we outsource this to cloud or high-end compute infrastructure because of the lack of externally facing networks within our industrial environment, right? They tend to be isolated and segregated from the internet. So then to tackle this, some of our work approached this by looking at lightweight machine learning models, right? So models that are part of the kind of classical machine learning group, if you like. For part of this work, we looked at the behaviors of PLC memory, like I mentioned in the previous couple of slides, so the evolution of PLC registers and their use in the application code, in order to provide highly deterministic models of the different states that PLCs can be in, right? We then use these models with lightweight machine learning models, such as k-nearest neighbor, support vector machine, and so on, in order to profile the attack behaviors that we would see, right? And we used real PLCs for this, real data. So what we found out is that essentially you can do, or you can achieve very high accurate detection using these models, right? You don't necessarily need to have complex AI, complex deep learning in order to detect attacks that target OT and the underlying components. And this is particularly the case if you take into account the computational benefits that you get with lightweight models within resource-constrained environments. So you see the box plot on the bottom, your right here, where most of these models achieved inference or detection inference times of under a second. Now, what do we do though if we have more complex behaviors to model, right, or more complex and stealthy attacks to detect? Okay. So the integration of multimodal data, so different data modalities, right, has demonstrated superior accuracy and also explainability of underlying CNI and OT attacks, right? And we've demonstrated this through some of our work where we explored the differences between looking at data modalities in isolation and then looking at the relationships between these modalities, so that the bar chart here at the top, specifically the green bar you're looking at on the left, this is the false positive rate when we just look at sensors and actuator data, right? So this achieves around about 6% false positive, keeping in mind that the score has been normalized. This is quite high, right, in a system. Whereas when we include additional modalities, so in this case network data, we achieve an order of magnitude better performance with false positive rates, as in lower than using single modalities, right, in this case 0.6%. So there's a clear benefit to including different data modalities, but of course this comes at a cost. And the cost is in terms of the computational overload, right? So you see in the line graphs here, as model complexity increases, and model complexity is represented by the four models at on the x-axis of these graphs, getting more complex from left to right. We achieve better performance in terms of detection, but of course at a cost of inference time, right? So in order to actually achieve the inference times that we saw using the lightweight machine learning models, we need to have better compute power, better resources to do this, and more optimized models. But of course, this is a general problem. It's not necessarily specific to CNI. This is more general to AI and the use of complex deep learning more generally. The one benefit that I will highlight here, though, of using multimodal data along with deep learning approaches is the ability to provide explainable outputs, right? More informative information for operators and analysts to use that will then enable quicker triaging, quicker incident response, and more informative recovery. So, how do we integrate explainability into these approaches, right? Well, firstly, we need to be able to model the data modalities that we're talking about through some sort of approach that captures these relationships, right? And graph-based approaches, we've heard a couple of talks today about these, are a natural candidate for this because of their ability to capture the relationships between data, but also to support kind of the understanding of complex system behaviors evolving over time, right? So let's take an example. So we've got a toy industrial control system environment here and a PLC. We would take our PLC and extract the various data artifacts from different data modalities, right? This might be logs, could be network packets, could be memory registers that have links with the sensors and actuators. And we then embed these pieces of data as nodes within a graph and draw edges between them based on the relationships that we see between the modalities, so such as the use of registers on the PLC itself and then across the network between PLCs. So we can then extract features from these individual nodes, these artifacts, and then use these to provide as an input, if you like, in our deep learning models. But fundamentally, what this offers us is the ability to use these graph representations such as this to better understand the evolving and complex relationships and behaviors within OT attacks. So I'm going to finish with this slide just as an example of some of the work that we're doing and one of the approaches that we developed in the Glasgow Cyber Defence Lab that captures the relationships between these modalities and that can be used for detection. So in these figures, what we have is nodes that represent either network packets or memory registers from the PLC. And then we draw edges and interconnectivity between these registers and the network packets, depending on whether a packet contains data to do with that specific register. So it might contain data to do with a temperature sensor or a pressure sensor and so on. So you see that what we find is, if we look at the kind of baseline first, that you get these clusters of kind of highly dense register usage, right? And we can use these structural properties to then detect unseen cyber attacks, right? As you can see here, when we then target a new register on the PLC that isn't used within the normal behavior, you get this new cluster that we can identify and then extract more generalizable metrics for detection about the actual structure of the graph itself. And that brings us to the end of the talk. Thank you very much. As Dimitri said, we're on stand G3, so please come and have a look and have a chat to us if you're interested. Thank you.